Briefly about high-performance computing. So, a computing cluster, what is it? Well, it's actually several computers, or nodes that we call them, working together. So it forms sort of one supercomputer, you could say. And the reason we do this is, of course, increasing the computing power, both in terms of memory, internal memory, that can be how big, sort of, how much data can you handle at once without using the disk, and also by parallel computing, using many processors to increase the speed. So both big data in terms of memory and also bigger speed, you could say. If you look back at the history of computers, we had what's called the Moore's law. It's approximately every 18 months, I think, there was a doubling in computing capacity for many years. And this sort of leveled off a few years ago because we reached a plateau, you could say, limited by basic laws of physics. So computers don't grow much more efficient these days. They are the same like they were like 10 years ago. So the only way of increasing computing power now is to just put many of them together and make them working together to increase the power. And high performance computing is used in all sciences and also outside science, of course, in the internet world. How big is the computer, the Orion, for instance? Well, if you look at an ordinary laptop, I think my laptop is pretty ordinary. It has 16 gigabytes of internal memory, and it has a processor with 8 threads. So I can run up to 8 sort of parallel processings. I think this is pretty average, or perhaps a little bit above average, but your computers are probably in this range. In the Orion cluster, one node can have up to 1,000 gigabytes memory. So that's much bigger, you can see, than a laptop. It's like more than 10, close to 100 times bigger. And up to 80 threads, 10 times faster, you could say. So, and this is one node, and the Orion cluster consists of several nodes. Not all of them can take this much memory and this many threads. It varies between the nodes. Outside NMBU, we have the National Facility for High Performance Computing, which is called Sigma-2, and it actually consists of several clusters. Fram, Saga, Betsy. These are different clusters located in different. Fram is in Tromsø, Saga is in Trondheim, Betsy I think is also in Trondheim, or is it Oslo? Yeah, I'm not sure. They are located near universities usually, but it doesn't really matter where they are located because we can access them from everywhere if you have an account, just like we do with Orion. Each of these are much bigger than Orion. So Orion is small, but it's also local, right? So it's only us at NMBU that uses Orion, while these ones here are used by everyone in Norway, and not only all the universities, but also some companies and for instance, the Institute of Meteorology. The weather forecasts are computed on this. So, but using them is quite similar. So even if Orion is small and nice, using it is quite similar to using any of these ones. So that's nice, right? What you learn here is transferable to the Sigma-2 national platform. Before I move on, I would like to say a few words about this one here, Betsy. That's the latest of the clusters in Norway and also the most powerful one. The name here, where does it come from? Why is it called Betsy? Well, Betsy is actually Elisabeth Stefansen. And who was this woman? She was actually the first female mathematician in Norway. She graduated in Switzerland, in Zurich, approximately at the same time as Einstein, around 1900. and to become a sort of mathematician. And then she came back to Norway, and she was actually a teacher at NMBU, or what was then, it wasn't called NMBU at the time, but in Ås. She was working here in Ås as a mathematician and teaching the students in the early 1900s. So it's nice to know that the biggest computer in Norway, we have some paintings over at the administration building if you go down there and have a look. Let's have a look at some words we should know. A node I already mentioned. A node is one of the computers in the cluster. They typically have cryptic names like CN1, CN2, etc., etc. CN for computing node. It doesn't really matter. We are rarely concerned about which node we are using, right? We will see later. There is, however, one node that we are very often meeting with, and that's the login node. Because each time you log in with the terminal window from either your Windows or Mac, you log into one particular node called the login node. And this login node is never used for heavy computations. It's meant to be used only for simple file handling and testing and running small jobs in order to test that things work. And whenever you start your big jobs, you will be using one of these other nodes. We also log in with RStudio, and then we are on some computing node actually. So it's only when you log on in the terminal that you are using the login node. But again, it doesn't really. This is not something we think much about, right? To us, everything looks the same. Different nodes have different features. For instance, some software will only run on some type of processors and so on. But this is something we will not deal with in BIN310. We will only run software that typically runs on any node. But if you have taken some courses in machine learning and neural networks, some of these neural networks, they will need some special type of processors, for instance. Yeah, nodes are also grouped into partitions. So we have the small mem partition for small memory usage. And that's where we typically run our jobs, in the small mem partition. One of the nodes in this group is what we typically use. Sometimes when we need a lot of memory, then we have to use the huge mem partition. Some few nodes has some extra memory. So if we need more than around 100 gigabytes, we use the huge mem nodes. Otherwise, we use the small mem. And that, I think in this course, we will almost exclusively use the small mem. And in microbial genomics in general, we rarely use the huge mem because the data sets we have in microbes, the microbial genomes are small, right, compared to the eukaryotes. So the data sets are also smaller. The exception is for metagenome data, where we sometimes have huge data sets, and then we need to use the huge mem. But I'm not sure if we will need that in BIN310 this year. We try to keep our data sets smallish in this course, right? Because otherwise we are that many people, so we can't do heavy computations, all of us, at the same time. And also I can say we will never use more than one node in our jobs that we will submit in this course. This is clearly possible, but we will never use more than one node. So you have to use multiple nodes for the really big jobs, but not for us. Each node has a number of processors. So that's the unit that processes data, right? And each processor also has a number of threads again. And the more threads you have, the faster you can compute, you could say, as a general rule. the processors in the Orion nodes are quite similar to what we have in our laptops. So it's not like the processors are faster. It's just that we have many more of them. So we can run things in parallel and increase the speed. But I have to say that the speed increase is not that big. The memory is much more important. To use many threads, your software must be made to utilize this. And this is quite important to remember, because you should always check out if the software allows you to use many threads. Right? Not all software do that. For instance, when you run R, you typically run one single thread. You can use multi-threading in R, but by default it's a single thread. So at least it was. I'm not sure anymore, really. But some softwares will not utilize multiple threads, and then it's a waste of resources to allocate many threads if you can't use them. Right? Your job will still run, but it will only use tiny fraction of what you actually reserved that could have been used by other people, right? So please check this out. Don't use many threads if your software can't make use of them, you could say. And also, speed is not growing linearly by the number of threads. Far from it. If you go from 1 to 2 threads, double the number of threads from 1 to 2, then you double the speed more or less. But if you double from like 40 to 80 threads, it's usually only a slight increase in speed, which is not sort of proportional at all to the doubling of resources. So it typically levels off like this, right? If you have number of threads along the x-axis here, when you start out with very few threads, then using a little bit more will give you more speed. But as the number of threads are increasing, then adding even more threads will give you less and less benefit, you could say. So it's a waste of resources to operate out here in such a software. And many softwares, most softwares I would say, will behave like this in some way. So be aware of this. We will typically use 10 threads in BIN310. We will typically be down here because that's fast enough for us. A job, that's the process that we start, the computing process. And each job that we start gets a number, which is the job identifier. And this is important in case you want to cancel your job. So then you need this job ID. And you can see in my documents, module 2 document, how we can do this. Yeah, whenever we start a job, we submit a request to the queuing system, we say. All these computing clusters has a queuing system. And this is for using the resources effectively, because if everyone started their jobs when they sort of typed them in, it would mean that most jobs will run at daytime, nothing at night when no one is at work, right? So this is for spreading this out over the full day and making use of the resources effectively. So Orion uses this Slurm queuing system, which is exactly the same as the Sigma 2 clusters are also using. So that's nice. And the queuing system decides which node we will be using. So we can specify to some degree which node we will be using, but we will not do that in this course. We will only specify how much memory we need to complete this job, which partition will we use, usually the small mem partition, and how many threads will we reserve for computing. So it's actually the first and the last one here that we have to sort of make up our mind about, depending on the software we are using and the dataset we have. And remember, we are many users, so never ask for more than you need, because this will be reserved, right? So if you reserve a lot of memory and a lot of threads, no one else can use this while your job is working. And if you don't use it effectively, it's a waste, right? So please try to be a little bit modest here. And I think that the memory we need is usually very small in this course. And also, as I said, the number of threads, either 1 or 10, I think. Sometimes we reserve only 1 thread because the software we use cannot utilize more than 1. Then it's silly to ask for more than 1. And if we can utilize more than 1, we usually use 10 in this course. But of course, you may change this, but for this course, I think we will stick to that. Files and folders. First, folders and directories are just 2 words meaning exactly the same thing. So I sometimes use folders, I sometimes use directories. So when you log in, you always come to your home directory, right? We saw that in the first module. And here is the home directory module, home directory. For each one of us, we just replace this one with the username, and the rest is the same for all of us. And the home shell variable, the environment variable, just contains this address for you. So you can, so if I refer to this $home when I'm logged in, it means my user home, right? But if you use exactly the same $home when you are logged in, it refers to your user home. You can have up to 200 gigabytes of data under your home, and this will be more than enough because we will not store data really under our home folders, because all the data will be on a course folder that I have shared with you, and you will not copy the data from that. You can only read them. So we need 1 copy of each dataset. And the only thing you will store under your home is the results from computation. That's usually much smaller. You also have the Scratch directory. What is this? This is a sort of a mirror, you could say, to your home directory under a different folder here, the Scratch folder. So, and again, it's a username that names your Scratch folder. And you have also the Scratch environment variable that refers to this one. So what do we use the Scratch for? Well, we typically store primary output from our computations in this folder. So, and why is this? Some of the software we use, they produce a lot of output. Thousands of files and folders sometimes. And if we stored everything under home, it will soon fill up, right? So what we do, we write the output to the Scratch folder, Scratch directory, and then we just copy whatever we need from this to our home. Because usually we only need 1 or a few files from this mountain of output. And then we delete this mountain of output from the Scratch disk. So don't use the Scratch disk as a storage of data, because there is no backup on the Scratch disk. So in case something happens, it's lost forever. It's only meant for temporary storing things that you are not so concerned about. And output from computation is of this type, right? Because if it's deleted, we can always compute it again. But please remember to delete the old results from Scratch. There is no automatic deletion of it. You have to delete it yourself. Otherwise, it will fill up. Even if the Scratch disk is huge, it's not limitless. It says no limit here, but of course there is a limit somewhere to how much rubbish we can have on this Scratch disk. So please, once you have done with your computation and you have copied what you need from that output back to your home, then you just delete the whole output, freeing the memory. We also have another temporary folder that we may all use. It's under this path here, and we can refer to it by $tempty. And this is for temporary. This is used during computations, because some software tools make use of a temporary folder during computation. It means that I write to this folder and read it back again, and write to this folder again and read it back again, multiple times usually, back and forth. And then they delete it in the end, right? The software is made to use this temporary folder and then delete everything it put there before it ends, right? And then we use this folder here because it's faster to read and write to, but it's not like we have a separate directory with our own username here. This is something we share with everyone. And it's meant for this type of usage. So we will sometimes make use of it, but the scratch disk we use sort of all the time, and our home. So the working on an HPC. First of all, the first thing we notice, of course, is there is no graphical interface. There is no desktop. Files are not shown as small images and folders and stuff. So this has been eliminated, you could say, because it's a waste of resources, and instead we have to use the command line. However, on Orion we have the RStudio login, which is sort of a graphical interface, right? We get the RStudio shows us files and folders, and we can click on them and do stuff. But this is if you go, for instance, to the Sigma 2 clusters, you will not have the same RStudio opportunity as we have on Orion, at least not yet. So the command line is what we will use, and we should learn to use the command line, because this will always work, right? This graphical interface is not always there. So you need to know some Unix commands to survive in this environment, right? And we looked at something in the first module, and that's really all we need, but we will use it repeatedly throughout, so hopefully something is something that is stuck in your mind for the future. To start a computational job, we need a shell script, a small text file with some Unix commands. And we will see in detail how we make these shell scripts in module 2. And please remember, we are many users on any HPC really, so try to behave accordingly. Never start experimenting with how much memory you can allocate or many threads you can. Try to be modest and don't do things that you're not supposed to do. There are some administrators with all rights, and they can actually throw you out of the system if you start misbehaving. So please don't do that. Okay. A short but precise description of the quality scores in FASTQ files. So here we can see an entry in a FASTQ files. It contains always 4 lines of the text file. The first one is a header line. It's just some code for this read, right? The second one is the sequence itself. This is the read. This is the DNA sequence. 1 line. We only see the first part of it here. Then there is what we call the plus line, which is usually empty, but it could also contain some extra information that was not in the header. And then the 4th line is what we call the quality line. And always, whenever you have a read of a certain length, you have a quality line of exactly the same length. So it means that any symbol up here has a quality symbol down here. So if you look at these 3 symbols here, AAT, what is the quality of these 3 bases? This is what we find in the corresponding positions of the quality line. And these 3 symbols indicate now the quality of these 3 bases. How much can we trust that these bases were actually sequenced correctly, we could say. That's what this quality line is trying to tell us. How much can we trust the sequence, the DNA sequence here, position by position by position. So what we'll actually show now is how these three symbols here correspond to some quality scores, which in turn also correspond to probabilities of error. So these are actually the probabilities that we have an error in the first position. This is the probability of an error in this position, and this is the probability of error in this position. And they are all told us by these symbols here. How is this working? We need the ASCII coding table to understand this. There is in this table an integer value behind each keyboard symbol, plus some additional symbols that you don't see on the keyboard. The first visible symbol is exclamation mark, and it has the integer code 33 in this table. This quality score, which is sort of related to this to any symbol in this in this quality line, you get by replacing each quality symbol by its ASCII value and then subtract 33, which is here. So it means that these three symbols here, smaller than, @ and capital F, if you look them up in the ASCII table, you will find that they have these integers in the ASCII table, 60, 64, and 70. Then from each one of them, we subtract 33, right? And you get the quality scores. These are the quality scores behind these three symbols. So the symbols are converted into quality scores. From quality score Q to probability of error, it's this very simple formula here. The probability of error is 10 to the power of minus Q divided by 10. So you can see that again we have these three symbols. We know that we can turn them into the quality scores, the Qs. These are the Qs, right? And then we can just plug each of the Qs into this formula here and get these probability values. So this is actually the way from the single letter symbol to these numbers here. And notice the reason we have this coding is of course that we want this quality line to have exactly one symbol for each base in the read. Right? For each DNA symbol, we have a quality symbol. If we use these numbers here, it will be a horrible mess, right? The quality line will contain a lot of numbers and zeros and blah, blah. I mean, we couldn't see where one number starts and the other ends, right? So that's the practical reason for this coding.